All right, everybody. We are going to be talking today about related rates. And there are word problems. So you need your calculator and the other notes sheet that I have on Canvas. But they're not difficult. They're going to involve some geometry formulas that you may or may not remember, but you'll be allowed to put them on a note card come the test. So related rates are problems involving variables that are changing with respect to time. Okay, very, very important. And what I want you to remember is we're going to do implicit differentiation. And if you remember with implicit differentiation, whenever we would take the derivative of y, we would attach a dy dx, its chain. Because everything we were doing was respect to x. Well, now we're going to respect time, which is t. So if it doesn't have a t, you have to attach the chain, which would be, and we'll call it d dt, whatever the variable is. It could be dv. I'm going to call it d variable. The variable dt, dA dt, dH dt. And so that's what's going to happen when we start doing these word problems. You're going to see we're going to need to attach it with respect to time. So in this first example, it's not a word problem, but it's just showing you some notation because you really never want to fear calculus because of notation. But here's what this one is saying. Find the dy dt evaluated at x equals 3. That's what that means. Find dy dt evaluated at x equals 3 and y equals x squared plus 3 if dx dt is 2. So they're giving us some information here. They're giving us x to be 3. They're giving us dx dt to be 2, dx dt to be 2. And they're also giving us a formula. This is really where we want to start, this formula right here. So we're going to write that down, y equals x squared plus 3. And we're going to use implicit differentiation to take the derivative of this, but with respect to time, with respect to t. So anything that doesn't have a t, this doesn't have a t, this doesn't have a t, this doesn't have a t, anything that doesn't have a t, you need to attach the variable dt, whatever the variable happens to be. So for example, if I were to take the derivative of y, it would just be 1. But since I took a derivative of y, I would write 1 dy dt. And honestly, you don't need that 1 there, but I'm just showing you that's the derivative. For x squared, you would take the derivative just like you normally would, 2x. But because it was not a t, you're going to attach whatever the variable is, dx dt. Now 3, the derivative of any constant is 0, so I don't have to attach anything because 0 times anything is 0. But what I've just done right now is I've taken my derivative, and now I'm going to plug in the things that they told me already. So they told me that wherever you see an x, that's going to be 3. And wherever you see a dx dt, that's going to be 2. And you're going to find dy dt. So we're going to find dy dt. 2 stays 2. X, they told us up here, x is 3. And dx dt is 2. So that is my answer, 2 times 3 times 2, which is 12. And then you could put your units after that. But this is the general idea behind related rates. Now, before we get into the word problems, I just want to talk to you about some clue words for derivative. So, for example, height is changing at a rate of. Height is changing at a rate of. That phrase, changing at a rate of. But if we're referring to height, that would be dH dt. Volume is decreasing at a rate of. Volume is decreasing at a rate of, or increasing, dV dt. The change in area, dA dt. How fast is the rate of the radius changing? And that would be, we'll call it dr dt. These are things that you'll see on what we go through today. Okay, So get out your sheet, the notes, and let's just do some of these examples together. And I have a calculator on my phone because my calculators are all at school right now. So I'm doing this from home. I'm going to just use my phone calculator. It should work. All right. So here's just the basic steps that I would write in like little boxes for you. And this is what we'll be doing for all the problems. A pebble is dropped into a calm pool, causing concentric circles. The radius of the outer ripple is increasing at a rate of. Do you hear that phrase? Increasing at a rate of. When the radius is 4 feet, what rate is the total area changing? Again, those phrases are coming up. So just to kind of give you an idea, we've got this pebble going in, we're forming a circle, radius. So you should know two formulas for circle. One is area of a circle and one is circumference of a circle. Since they're asking us about area, we should use that formula. The area for a circle is pi r squared. Now, we're going to just take a derivative of this with respect to time. So the derivative of A is dA dt. That is the rate at which the area is changing. The derivative of pi r squared, remember pi is just a number, bring that 2 times the pi, so that'd be 2 pi r, now to the power of 1. But because this is an r, we need to attach dr dt. That's the rate at which the radius is changing. So now that I've gotten this derivative, let's kind of go back and read through our story again. The pebble is dropped. The radius of the outer ripple is increasing. The radius is increasing. That's dr dt right here. When the radius is 4, what rate is the total area changing? That's dA dt. So we know dr dt is 1 foot per second. We know dA dt is what we need to find. And so the only other thing we have is the radius is 4 feet. So that's just r equals 4. So we're going to take this information and we're just going to substitute it in right here. dA dt is what I'm trying to figure out. 2 times pi. The r is 4. The dr dt is 1. And you can keep it in terms of pi. Actually, I like it that way. So this is 8 pi. And area is always measured in squared. So dA dt would be feet squared per second. And that's just a very general one, but that's how we're going to do most of these problems. You're going to have some kind of formula, some kind of equation. You're going to take the derivative of it with respect to time, substitute in your information, and solve. All right, let's do another one. Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change, that's supposed to be change, of the radius when the radius is 2 inches, okay? So a spherical balloon would be something like this. And you have an R, it's air is being pumped in. So we're talking about the volume of a balloon. So if you don't remember your formula for volume of a balloon, it's 4/3, or volume of a sphere, excuse me, 4/3 pi r cubed. All right, now we're going to take a derivative of this with respect to time. So this would be dv dt. 4/3 times 3 is 4 pi r squared dr dt. You always have to attach the chain. All right, now let's kind of go back in our story and see if we can see this. This again is the rate of change of volume. This is the rate of change of radius. So let's see again what we're trying to solve for and what we're given. Air is being pumped into the balloon at a rate of. Air is being pumped into the balloon. That's the volume is changing because the air being pumped in. What also gives it away is cubic inches per minute. Cubic is volume. So this right here is your dv dt. Find the rate of change of the radius. That's what we're looking for. We're looking for dr dt, the rate of change of the radius when the radius is 2. So we're going to substitute these values in here. So let's see what we can do. dv dt is 4.5. 4 equals 4 pi. R is 2 inches squared. And dr dt is what we're finding. So this is going to be 16 pi. And we're going to just divide it over. So 4.5 divided by 16 pi is your answer. And we're talking about a radius, so that would be, units would be in inches per minute. But just to show you something, if you put this in your calculator, because some students put it in wrong, and I will mark off wrong. If you just do 4.5 divided by 16, and then do pi, that is the incorrect answer, if you can see. I know there's a glare. Let's see if I can move it that way. No. 0.88 is the incorrect answer. What you need to do when you type it in, you have to hit 4.5 divided by parentheses 16 pi. And then close the parenthesis. Let me show you what that looks like. Glare is pretty bad. And then hit enter. That is the correct answer, 0.09. 0.09 inches per minute. So be very careful how you leave it. But if you left it in terms of pi, I'm fine with that. All right. Do this ladder problem. They love ladder problems. A 41-foot ladder is leaning against a wall, and the top is sliding down the wall while the bottom of it slides away from the wall. Okay. So let's do this real quick. Let's kind of draw this. We got this ladder leaning up against a wall. We know the ladder is 41 feet. Look at what shape I've drawn. I have drawn, looks to me like a right triangle. Now, I know about area. Area would be okay, but we're talking about lengths of sides of the triangle. So I would use good old Pythagorean theorem. A squared plus b squared. We know the c. And I would take a derivative of this. So let's take the derivative of a squared, which is 2a, but we have to attach dA dt, the rate at which it's going down or across, whichever one you want to call a. This is 2b dB dt. And 41 squared is just a number, so I'm just going to put 0. Okay? So we could call this a and this b. That way we can make more sense. So a is the length up the wall, but dA dt is when it's sliding down. And b is the length of the floor, the bottom, and dB dt is sliding away. Okay. Now, with triangle problems, there's always two going on at the same time. So they had already told us, we'll go over here, the ladder's never going to change. It's always going to be 41 feet. But they did tell us right here, how fast is the top sliding when it's 9 feet above the ground? So we do know that this is 9. Well, that's good because we can actually figure out this length right here. And again, if this is A, this is C, I can figure out this is B. And if you don't know this, this is a famous Pythagorean triple. This is 40. That's my B. So that's very helpful because now I can substitute that in for B. So 2 times 40. And then I just need to kind of read back on my story and figure out what else do I know and what other piece of information I have. Well, I do know A, so 2 times 9. Let's see if I have anything about dA dt. Now, again, what is dA dt? dA dt is the rate at which I'm decreasing down the wall. A 41-foot ladder top is sliding down the wall while the bottom of it slides away. So the bottom of it slides away. We know that information. So that's our dB dt, the bottom sliding away. So that's 4. dA dt is we're trying to figure out how fast is it sliding down. So now we know everything. So that's 18 dA dt. And this is, what do we got? 8320. Whoops, plus 320. Oh, and then one more thing that I forgot to do. Well, you're going to find out, actually. Never mind. 18 dA dt equals negative 320. And then 320 divided by 18 is 17.8. And we're talking about feet per second. Now, here's the thing. I got it negative. Why is it negative? Well, remember, that's the rate at which we're sliding down the wall. So it's talking about position and going down the wall. All right, let's try another one. Gravel is being pumped. I love cones, by the way. Gravel is being dumped from a conveyor belt at a rate of 100 cubic feet per minute, forming a conical pile whose base diameter is 2 times the altitude. How fast is the height changing when the pile is 12 feet high? So you have this cone that's coming up because of gravel being dumped. If you don't remember your cone formula, it's volume equals 1/3 pi r squared h. Now, just a little side note, you might want to make note of this. For cones, the best thing to do is to convert your r to h or your h to r. Convert all the radius to heights or convert all the heights to radiuses. Now, what does that mean? Well, they told you something here. The gravel is being dumped from the conveyor belt at 100 cubic feet in a conical pile whose base diameter is 2 times the altitude. The base diameter, this whole diameter, is 2 of these. So I didn't really draw this to scale. So instead of calling this R and R and this H, right, this base diameter is twice the altitude. So this would be an H and this would be an H. So that means my R and my H are the same. Now that's helpful because I'm going to go back to this formula, and you always have to do this before you even begin taking derivative. You have to rewrite this formula so that it's all R's or all H's. So I'm going to go volume equals 1/3 pi. Now, which one do I choose? Well, it depends on what they ask you. How fast is the height changing? So I want to make my R's into my H's. So I'm going to change R to H. I'm going to square it, and I'm going to have the other H being multiplied by it. So what does that clean up to be? Well, that's 1/3 pi H cubed. Now I can take a derivative of that. So the derivative of volume is dV dt. 1/3 pi H cubed, 3 times 1/3 is 1, so it would be pi H squared dH dt. And now I'm going to go back and fill in what I know. The gravel is being dumped at a conveyor belt of 100 cubic feet. That is the rate at which it's being dumped. And again, what gives it away is cubic. So this is 100. Pi stays pi. H, they said, how fast is the height changing? That's dH dt. That's what we're trying to figure out when the pile is 12. So 12 squared goes here. Don't forget about that squared, dH dt. And so that would be 100 divided by 144 pi. But like that. We're doing so good. I know this is a longer lesson, but it will be helpful, I promise. All right, next one. Told you I love cones. A conical tank with a radius of 6 centimeters and a height of 24 centimeters is leaking water. The water level is decreasing at a rate of 30.4. What is the rate of change of volume when the height is at 9? Okay, so again, you have this cone. I'll make it different this time. And we were actually told that the radius is 6 and the height is 24. Now again, you're not going to use those numbers. You are going to convert R's to H's or H's to R's depending on what they want. Since they want us to talk about height here, I'm going to convert my radius to height. So if I call this H, how is 6 related to 24? Well, 6 is 1/4 of 24. So this is really 1/4 of H, 1/4 of 24. This is what you're going to be using in your formula. So again, my formula for cone is 1/3 pi r squared H. So now I'm going to substitute in, instead of r, I'm going to put in 1/4 H. So 1/4 H, I'm going to square it, and then also don't forget about the other H. And I'm going to clean that up. So 1/4 H squared, that's 1/16 H squared. And 1/16 can multiply with the 1/3 and become 148 pi. And then you still have the H squared and the H, which makes H cubed. Again, all I did was 1/4 times 1/4, which is 1/16. I'm allowed to do it with the 1/3, so that becomes 148. And then H squared times H is H cubed. And now we can take a derivative. dv dt. 148 times 3 is 1/16 pi H squared dH dt. And now I'm going to substitute in information that I know. Let's see. The water level is decreasing at a rate. The water level, that's the height right here, and it's decreasing. So we're going to find the volume. And the height is 9. And the water level is decreasing, so we're going to need to call it negative 30.4. And we can use, a calculator. Again, sorry for it being so bright. I can adjust it down a little bit. There we go. So 1/16 times pi times 81. I like to put them in parentheses, times negative 30.4. And I have a negative 483.5. And that would be in centimeters, cubed per minute. That's the rate at which it's decreasing, changing in the volume. All right, a little business applications, 2 questions, and which will be in homework, and then we're done. A company's revenue from selling X units of an item is given as R equals 1100X minus 2X squared. If sales are increasing at a rate of 55 units per day, how rapidly is the revenue increasing in dollars per day when 220 units have been sold? Okay, and actually here's our answer. So what you just have to do right here is just simply take a derivative. So the derivative of R would be dr dt with respect to time. The derivative of 1100x is 1100, but wait, don't forget dx dt. A lot of students were forgetting that. The derivative of 2x squared is 4x dx dt again. And now let's substitute in what we know. Sales are increasing at a rate of that. So which one is that? Is that dx dt or dr dt? How rapidly is the revenue increasing? Isn't that what I'm trying to find? So isn't that dr dt? When 220 units have been sold. That's your x. This is your dx dt. Because that's the sales rate. So it would be 1100 times 55. That's the rate at which it's increasing. Minus 4 times x, which is 220, times another 55. And we can check it on our calculator. Hopefully we got 12,100. So 1100 times 55 minus 4 times 220 times 55. 12,100. 12,100 would be the revenue in dollars per day. All right, and this last one, a little bit tougher. And what's tough about it is honestly just the derivative. Okay, A company selling widgets has found that the number of items sold X depends on upon the price P at which they're sold. According to the equation, X equals 90,000 over the square root of 6P plus 1. Due to inflation and increasing health benefit costs, the company has been increasing the price by $3 per month. Find the rate at which the revenue is changing when the company is selling widgets at $120 each. Okay, so remember formula for revenue. It is price times your demand equation, or X times price, or price times X. So, and since our X is already given to us, we're just going to put that there. So price times X. And we're going to clean this up a little bit. So this would be, the P is with the 90,000. And this square root, I'm actually going to bring it to the side and call it 6P plus 1 to the negative 1/2. Okay? Now, I'm going to take a derivative of this. And remember, it's R. So that derivative of R would be dr dt. So we'll do that. Dr dt right here. Now this is a product rule because we have two functions, this one and this one going on at the same time. So let's see if we can do this and remember. So first, 90,000 P first times the derivative of this, that involves a chain. First times the derivative, which would be negative 1/2 times 6P plus 1, and then subtract 1 to the negative 3/2, times the chain, which is 6. Oh, but wait, times dp dt. Woof. Let me put a parenthesis around here because that looks like minus. So let me go through that again. That was first times the derivative of this. Remember, this is like u to the negative 1/2. So you have to do the derivative of that would be negative 1/2 u to the negative 3/2 times the chain, but also times dp dt, because we're talking about a different variable here with respect to time. So first times derivative of the second plus the second times the derivative of the first, which would be 90,000. Again, but of a p, we would have to attach dp dt. Okay, now I like to clean this up. This is not looking particularly fun for me, so I like to clean this up. You don't have to, because you can put it all in a calculator, but negative 1/2 times 6 is negative 3. And negative 3 times 90,000 is negative 270,000 P. So I'm going to write it like that. And then put 6P plus 1 to the negative 3/2. And then dp dt. And then I'm just going to put the 90,000 in front here. Times 6P plus 1 to the negative 1/2 dp dt. And honestly, you could do some factoring here, but I'm just going to plug in the information from above there and just kind of let my calculator do all the work, to be honest with you. Due to inflation and increasing, let's see, the company has been increasing the price. Which one of these is increasing the price? Well, that's dp dt. Find the rate at which the revenue is changing. That's dr dt. When the company is selling widgets at 120, that's your price, P. Okay, so again, here's what we've got. We've got negative 270,000 times P, which is 120, times 6 times 120 plus 1. Well, 6 times 120 plus 1 is 721 to the negative 3/2. dp dt is 3, right up there, plus 90,000. Again, 6 times 120 is 720, plus 1 is 721. to the negative 1/2, and then dp dt is 3. So look at that, a lot of stuff going on. But I'm just going to punch this into my calculator and let the calculator do all the work. You just want to be careful how you punch it into your calculator. You really want to put like a lot of parentheses around there. So let's see if I could do this well. Negative 270,000. I got to make sure I don't mess up a 0. Times 120 times 721 to the power of, that's a negative 1.5. Ooh, look at that, I already messed up. Go back. 1. There we go. 1.5. And then we're going to times that by 3. And I'd like to write that first part down, negative 5020.689. And then I'm just going to do this second part right here, 90,000. Sorry for the glare. Times 721 to the negative 0.5 power times 3. And that's 10,055 roughly. And then add those together. Let's see if it'll let me do that. Oh, it does. This plus that. And I get 5,034.6359, which is the correct answer right up there. All right, a little bit longer today, but you should be able to get all your homework done now.